So I guess we can start. So before I start, maybe good to mention something. Some additional material, as I promised. For those who want more foundations, you can look at my undergraduate course. I have undergraduate slides that contain basically all the proof that required to brush up all the statistics. So basically up to I think up to today's lecture. So all the foundation can be found there. Okay, it's there. And there's a natural notes. But anyway, any books would be useful. But and for some of people actually ask me at the end of the class, my class is too simple. So what can be done? What should be supposed to read if you want it to? What you should read if you want more? I mean, some people. I mean, I'm not saying anyone. Maybe I overheard hallucinate, but I mean, anyway. Actually, I have this question, but I will not recall who tell me that, but yeah. But you know who anyway. I mean, I think you know who. But anyway, but who econometrics is so if you want this Stock and Watson would be the one that you want to go for more foundational. I mean, it's easy to read. I mean, as a master level, you can read because it's usually a senior undergraduate. You can read that textbook, Stock and Watson. And also the Root-Rich one is also fine. But if you think it's not enough, you can always go to the PhD graduate level. This book, this is always enough. Well, it's not saying that you should read that book directly. I mean, this like the encyclopedia style book is never going to be, especially this book, never going to be written directly. You would be, when you need to use it, you consult the book and check. That's how I do. I mean, of course, now I taught this class, and of course I have to read. But otherwise, if you're not teaching, you don't really. I mean, when you need something, you do it. Suppose I mean, in this class, right, we talk about regression on the Y, right? And the Y is usually a continuous random variable, right? But when the data is like not a continuous or discrete 0, 1, 2, 3, 4, 5, then you still can apply regression, but you will see there will be some issue, especially when you have a lot of zeros. And many of you are actually the IT manager, right? And when you have big data or stuff, and actually a lot of Y are 0. And when you run the regression, there's a lot of issue here. And that requires a regression for count data. And look at this book will tell you how to handle those situations, right? And say, for example, Y is also, we don't tell you how to do when Y is categorical, right? And Y is continuous. We hold this for the rest of a class. But when Y is categorical, then what happened? How can you do that? There's some way to do it as well, but it's way beyond our class to do it. But there are many things. And machine learning, actually, some of you asked me as well. I would suggest you read the first book, and then second, the first book is easy to read. I mean, I think when I first read, I spent 1 or 2 days, whole day. I mean, 48 hours, maybe you can finish that book. I mean, there's no particular math there. But this one, the next one will be very complicated. I don't think I have finished it, but this is a very classical thing. I probably also mentioned Python as well. There's an optional lecture that I will do for undergrad. I think the room is large enough. If you want to go, you can go. The 2 days are the same, so you can just go there if you want to. And also some of you actually asked in the class, what's the Chinese translation? So I actually asked the TA and also ChatGPT and also some other people to help me on this one. So I think that is most of the term that is already translated. If it's not, then you can email me. I and TA will do it, or you can comment on it to see what should be added there. What else I need to say? Yeah, I think that's all. Yeah, that's all. And I don't know whether you signed up here already. If not, then please write down your nickname or what, because I need to know how to, is it enough for that class? If not, then we have to schedule other venue to do that. I mean, because this room is not actually good for presentation, right? You want a big, nicer room to do it. Huh? The last, I think the second to last or the last one? 21st, right? 21st, right? So probably, I mean, I need to see how many groups are there, and then we try to book see if we have a nicer room to do it. What do you book? Oh yeah, try to see if that room is available. That one will be a good one. Yeah. I mean the one in the Sino building. If that is available, then we'll be booked a longer period, because 3 hours may not be enough if depend on how many people you are in the group. So probably we need more hours, then we cannot use this room, and then we have to figure out other room. Or maybe we can make it say after the exam, then makes it maybe even better, so that you don't feel pressure to do it. But we will figure out, I mean, depending on how many people, please fill that up if you have time. I mean, you can just write your nickname, is also fine if you don't want people to know who you are. Okay, as long as you know who you are. Okay. So as I said, I mean, let's continue our lecture. It's number 5, and I will very briefly review number 4, because that is the basis of what we will be doing. Okay, because today is like try to do some generalized regression. Of course, we'll go over the Python code as well. But before that, let us quickly try to be quick review, because you'll be doing quiz during the first break as well. I mean, try to see if you fully understand what's going on there. Regression analysis is the topic for last week we covered, and the main idea is try to understand how X and Y are related, right? And this is the single regression, and today we cover multiple regression. And the way to do is to model the expected value of Y based on X is a conditional, right? Based on X. And the two goals is, one is causal analysis. You try to interpret when you change X, how Y being changed, or we don't talk about cause and effect, is use X to predict Y, okay? And it can be X and Y change at the same time due to a cause set, but as long as X is useful, then it's fine, right? Just like, I don't know whether you know, but people look at stock market, right? And you notice when the Hong Kong stock market, one of the biggest predictor, is look at what happened in the US market last night, right? And you would tend to think, well, the US market drive the Hong Kong stock market, but indeed it's overall the market sentiment, the money, look at the future actually affecting is someone common in the background. But that is, but you should prediction, that would be the case you use, right? So that would be the idea. So when you run regression, usually we talk about parametric method is one of regression, but the book is very general, so we cover what we call much more advanced method called non-parametric. By non-parametric, the difference of the parameter 参数 is the meaning of you have make more assumption on what underlying Y and X are related, right? You just impose a condition in a parametric way, right? Of course, it make your life easier, but of course, when we make a mistake, then you make a much wrong, much bigger error, right? And non-parametric, of course, is less assumption, but of course, it's less accurate, right? And then the way you do the non-parametric method, which we don't even taught what's the methodology, but simply we motivate by the idea that you simply do 2 steps. Step 1 is divide the data. I mean, look at this one, right? Using a scatter plot idea, right? You just group the data point, right? And then use the within the partition according to X, and the prediction of Y is based on the average value of Y within the partition of X. right? Just the idea, just repeat what I saying. If I just do it to is here. If you have a partition, right? Basically, just you divide. Say this simple thing is, say, suppose you maybe just the left hand side, right? The left hand side like this, right? And you have many data points, but you can summarize it by the mean of within this region, right? And there's the simplest model you can think, right? Just like divide the data set into both halves, use the mean of the first half when you try to do the prediction, right? Just like this hotel, I think hotel prices, look at the data close and far, look at the close hotel, the price, and that with the prediction, okay, when it is close, right? The same idea you can do for more beans, okay? And the lowest is basically using the smooth curve to connect them all. And there are many ways to do it, but we are not telling you how actually being done, but we just say there's a black box technique, and the black box technique, I think the Python has already shown how you do this. The method is very simple, right? And just to go back to this one, because some of you asked me why 0 and 1, because this result actually gives you a 2D NumPy array, okay? And this is just trying to give you the first column, and this get the second column, because this is just X and Y. So this is how they been. Later you will see today when we produce confidence interval, we have the same thing, we have the same function. You'll see again. Okay. I mean, hopefully you will understand what's going on, but this is standard Python thing, so nothing very special. And the next is the regression. Okay. The regression is simply saying a line to fit the scatter plot. So it's important. So let me talk this again. Okay. The main idea would be just try to draw a line. You just change the intercept and the slope, right? Such that you minimize the vertical distance, right? The reason the vertical distance is because you use X to predict Y. The vertical distance is called the error, right? Is how accurate the measure is. And you square because you want to do the sum of them, right? And the alpha head and beta head, the formula there, but it's not important. No one care about the formula anyway, right? Because of the reason that the calculator or the Excel or Python or R give you the answer already, but you can see the intuition, right? It's correlation coefficient normalized by the variance, right? Because correlation coefficient is actually a measure of how X and Y related. Okay, and just to remind you how you would use this, because we see this again today, because this is the goal, right? And you would use the stat models API, okay, to run this regression. And the way we do it is usually this I show you in this way, but usually when you do it, actually use some data, right? So use the pandas to import from the CSV file, Excel file, and then just directly use it. Okay. And also you can see the code from the online, and that's how we do it. But the same thing is just some constant. We just create an object that's from ORS, and you just fit that in, and then just print the result. And the main thing is look at this coefficient, right? Look at the T or P value, depends on what you like, right? Look at the P value, and this is the main thing you want to look at, right? And of course, also look at R square as well as a measure of how fit the data they are. Okay, so this the basic main thing you want to look at. This is the code you want to plot how it looks like, right? Look, this is the plot that the blue is scatter plot, the original data, the red is the regression line. Okay, and do note that this is a idea of data analysis, right? The data you have is just the blue one, but based on your assumption, your analysis will come the red one. So the blue is no longer useful. The red one is the thing that you use for our analysis. Okay. And you want to generalize this from, say, data only 3 and 4, but you generalize it to 3.5 also works out. So that is the goal of the ORS. And we'll talk about this today again at the end. So this is the one of the main thing is you want to find the most underpriced hotel, right? Regression line and the highest distance, right, would be the most budget, most discounted hotel, right? Because this is the hypothetical line that what the price would be, right, was lower, right? So that would be how you find the best deal of that. And chapter 8 is about how you would want to transform your model from linear to non-linear. One of the main idea we do is to transform log transformation. Instead of x, say this one, we call log x or we call log y. It's still a linear regression. But the idea why we want to transform is the how x and y related, right? When you transform to log, by definition, it becomes percentage change, right? Is it the change matter or the levels matter? Okay, so that is the idea. And unless the theory tells you, then usually you don't know which one is better. But as I mentioned the last time, a visual looking would be a good thing. Is look at whether one should do transformation. Is it symmetric along the line? Of course, you can plot the residual plot, right? That is the usually you do is if you just don't know to look at it, you can plot the residual plot, right? You can easily look at the how y and y hat and plot that one and then see how they look at. But that would be the and besides the log, then you also have another way called piecewise linear, which essentially said is still more or less linear, but you kind of like you cut this into x into multiple section and you draw a different line there, and the line are connected. Okay, and the way to do it, I think the Python code is there. Okay, I'm not sure how often you use it. At least my understanding is this is not very often used. Okay, because the reason why it's not often used because you need to figure out what are the knots at the beginning, right? Of course, you can do in the chapter 13 to 15 we call cross validation. We tune the parameter that can be doable, but still it's not something that often we use. The more often used is what we call this kind of nonlinear polynomial, is more smooth. So here I have a contrasted one, but in general you can fit any n degree of a polynomial to fit that one. There will be usually a good one, right? And in general, you start from the linear, then you go from contrasted, so on and so forth. Then you will see how we do it, right? I mean, later you learn the machine learning, right? There are many ways to build a model, right? You can top-down approach or bottom-up, right? You can start from the easiest and build up, or you can come from the largest end you can imagine and cut it down. Then you know which way to go. But this is the way you select model. And of course, some of you ask how you select which one. Then the one easiest way is to look at the root mean square error, right? Look at the y hat square. That one we talk about that in the chapter 13. I think 13 that we will talk about those. And that is what we have covered last week. Is there any question? I guess after the long weekend and you may not able to record everything, but I hope it's okay. But anyway, we will see the quiz and how well you're doing. Okay, later. Okay, but don't worry. The quiz is simply from the last. I guess everyone get more than half, so it's a mini math. You got full credit, so there's nothing nothing need to worry about. So just try your best and see how well you're doing. So I think now we go to lesson 5. Okay. lesson 5 is the idea that actually just do hypothesis testing and confidence estimation for regression, right? Because we just tell you, okay, come up with the line. That's it, right? We didn't tell you, okay, is how to use the line, right? Because this is the model tell you, okay, this is the line, but how good the line is, we didn't do it, okay? And we didn't tell you the, we also mentioned that to do the t-test on that, but here we do it precisely how we do it, okay? So the idea is, okay, we have the line, then how do we do more? Because the line just gave us a point estimate, the single line, right? But you know, run the regression, there must be some stochastic stuff, error, something you didn't model, right? And how can you get better, right? Just like the sample mean, we just don't give the mean, but I give a range whether you're going to hit it, right? So the same idea, we will do the regression and do hypothesis, and we talk about external validity, okay? So as you would be expect, there's nothing new here because if you have large sample size, which usually you have with your your IT manager, and you would have a large sample from your data source. And when you run the regression, the central limit theorem usually apply. And that means that everything you do is a bell curve. Okay. And that's why you expect the CR slope is just plus minus 2 of SE. Okay. Because Y2 apply because of bell curve apply. If bell curve doesn't apply, then you can't do it. Okay. And probably you ask, if bell curve doesn't apply, you can actually do the bootstrapping. Right. So how to do it, actually, you should able to, I mean, it's not, I didn't put in a slide, but it's already in a Google thing, but idea is very simple. You just bootstrap the sample, okay, create, say, 1,000 sample. Each time you run a regression, when in regression, you have a 1,000 beta. 1,000 beta, you can plot a graph, or you can calculate the sample standard deviation of that, then give you the SE. Okay, is that clear? Okay, that is something you would do. I mean, because you don't trust the normal, then you have to calculate by your own. And there are some complication of how this is being calculated. And if you learn statistics or econometrics in the undergraduate level, then you notice what we call the homoscedasticity and heteroscedasticity. Okay, and what does that mean? And let me draw a graph. Maybe easiest to explain very quickly. I hope it doesn't take a long time. So usually, where's the pen? Usually when we think about a regression, right, X and Y, right, and you assume it's a parametric, right? So you assume X and Y are actually governed by alpha and beta plus epsilon, right? Alpha and beta are something we don't know, but this is how X and Y are related, right? And epsilon is the error term, right? The error term usually is what we call the simplest thing we do is assume normal, right? With zero mean and standard variance, right? There's the basic thing you learn the first course of regressions like this, right? And that means that if you do this, okay, actually means the following. You would say, look at this point x1, go up, right? And this is, the height of this is what? Alpha plus beta x1, right? But this is just a standard one, right? But you have to add epsilon, right? It's an error term. So usually you would see the textbook would draw it like this, right? The bell curve here, right? Most likely it's in the center, but the bell thing goes on here, right? And the classical definition is saying that no matter which point you're looking at, say x2, another number here, and you also draw the bell curve, okay? And the standard, the simple one would assume no matter which point you pick, okay, this spread is the same. Is that clear? So this is a simple one, but this may not hold, right? Because strong assumption here, right? Why the wave? Because this was what is something you didn't put in the model, right? Suppose this is like Y is the price, right? Maybe say Y is the education, sorry, Y is income, X education, right? This may be IQ, maybe where you are born, where your father and mother is, so something is not in the model, right? And likely that this thing have higher variance when you have high education, right? Some people maybe, I mean, we go to the Tsinghua or Beida, maybe actually coming from Longchuan, right? Maybe actually coming from very, maybe second generation of ABC, right? Then that is the idea, right? There's a lot of variance, so it's not constant. Okay, it's not constant. Then actually we require what we call the robust standard error. Robust means is very strong. By English means very strong. Okay, means strong means they would say if the variance is not constant, then still work. Okay, so usually the general advice is always use this one. This is just for learning, and for practice always use this guy. Okay, so that is the usually when you learn econometrics, that's what they do. Okay, and here I call robust, and if you look at you go to economic department, they will call white standard error. Okay, because econometrician white they discover, but it's earlier covered by, I think, by a statistician called Hilbert. So I think it's Hilbert white standard error. That's why this name is called. But anyway, but probably only you care is how to implement this in your Python. That's pretty very simple. You just use the covariance HC3, that'll be fine. And probably ask there's a free, so it must be have 0, 1, 2. Yes, that's 0, 1, 2, but we only care about the free. Okay. And you will see when robust is something like HC3. Okay. So that is the thing. And you do see that when I have HC3, the same data, this become 1. Okay. And this is much larger range. So basically saying that this data, this coefficient actually have no, it's not different from 0, right? I mean, because this is how you do hypothesis testing. I think I talked about this last class already, right? If you want to test this, the hypothesis is H0, right? Where beta is 0 or not, right? And this one you can't read out, right? Because the data actually, the interval actually includes 0, right? Also, again, the alpha is includes 0. Yeah, it also includes. So basically the regression for this is useless, right? So you'll be useful, the regression, if you look at this column, is it less than 0.5? Sorry, 0.05. Less than 0.05 is yes, then there's something to say. Otherwise, usually we disregard this regression. Okay. So this is the rule, but this is how you look at the table, right? So as I said, this is how you look at it, right? You want to test this. Okay. And just to remind you how we do that, right? We look at the beta, okay? Is it different from 0 or not? Of course, if your regression get the coefficient is actually 0, then you're done because you can't really reject it, right? But it's different from 0. You want to ask the question, how far away from 0 you want to reject, right? The standard way to do it is we have to look at how beta looks like, right? And beta actually looks like follow the student t distribution. It's kind of normal, but of a much larger tail, right? And try to see compare to the standard error, right? Usually asking is more than 2 or less than 2, right? If more than 2 standard error, then it's far away enough. If less than 2, then it's still not far enough, so we can't reject. So this is the standard. Is that okay? I think if you learn statistics, that's something you learn many times in the undergrad. So I don't want to repeat this. Is that okay? But the idea is looking at either you look at this p less than 0 or look at like whether it's more than or less than 2. Now, the absolute value, right? I mean, less than -2 is also fine, right? Because, right? The idea is this, right? Because, let me just repeat a little bit. Because under the sample is large enough, which usually you do, right? The beta looks like this. Under the null, you say beta is 0. Okay. And should be okay. And the data you get is like, is it far away enough, right? So far away enough, we will talk about actually this region, right? We just look at 2 SE of beta hat, right? And this is also 2 SE of beta hat, right? And if these are these 2 regions, right? And then we'll say rejection, right? And of course, you can take this, look at the T compared to the same thing, right? Either you look at this dimension, the beta itself, or look at the T, it's the same thing. Okay. I mean, this is undergrad. If you still don't get it, I suggest you just have to read the relevant material because I can't really talk too detail on that one. Okay, because of time. Okay. And here's the alpha, the same idea. There's nothing special here except the formula is a little bit different. Okay. So for the beta one, I mean, maybe probably I have to explain a little bit about why this formula looks like, although it's not really, we never use it, because the general one is follow the same logic, but I try to explain it a little bit. Here is looking at how the slope, how varies, right? Because this tells us if you run this regression, right? And there's many different beta you might potentially get, right? And when the error term is, which is the variation come from the regression, right? If large, right, then this guy is large, normal, right? And look at the variation of X, okay? The reason it appear here is because beta, right, you would divide by variance of X, right? Remember how we calculate coefficient of beta, right? So if your X is larger, then the beta is smaller. If you don't, it's asking the following. Let me try to show it to you. Okay, you compare 2 different cases, then you will see why that's true. Okay. Remember, the regression line is always pass through the center of data, right? X bar, Y bar. You draw a regression here, right? Okay. And probably the question would be, okay, you want to see why X bar larger, the beta will be smaller, right? So you can imagine that if the data X is like among this region, okay, compared to the case where data is like this. So you would say, I would say, when you run the regression, you will have much large variance for the green than the pink one. Why? Because depending on what you pick, right? You're able to pick this, then the much flip. If you pick this one, okay, you pick up some number, how much you can flip is not a lot, right? Because beta is depend on how like, but let me draw it, right? Because look at the green one. What you might get is like this, depends on what data you draw on, right? And it can be like this, right? But if you look at the pink one, right? There's nothing you can do because there's a data is here, the data is there. I mean, you can't really draw something very extreme, right? When data is a lot, right? it's much more spread out, right? Then unlikely that you can come extreme. Concentrated at one point, very close by, then it's like very likely, there's a lot of freedom there. But that is the intuition, but I'm pretty sure you learn it undergrad anyway. And here it's very simple, right? The more the data point, the less variation, okay? But don't worry, we are not using this one, right? We'll use the complicated one. But this gives the intuition why this is true, okay? And here I want to give you the intuition why the alpha is true like this, right? There's no problem. The higher the variance, the higher the alpha. That's definitely simple. And you ask this is also natural, right? Because there's more sample, right? That way back. And this variance, I think that is not difficult to see. The same idea here. But probably difficult is why X bar is increasing, right? You can imagine the simple thing is the higher the X bar, the more further away from the intercept, right? So that means that you are very far away from the intercept, right? So the data you measure, right, has much more variation, right? Because put in this way, you can imagine, just give intuition. So don't worry about it. We never use it in our practice, but just to give some idea, right? And remember the regression line passing through X bar, Y bar, right? So that has to be remember. And look at the case where X bar is very far away, right? Also, you pass through that. It can be passed through this and pass through that, right? But this one, you're very close, right? So the variation like this, right? But when you go back here, muchly expand, right? Because the difference here, travel long way, magnify, right? Just like butterfly effect, right? Something happened there, transgress to a very long path, even though take a long time, but it will turn out to be very big. But anyway, this is just showing you that how to understand the formula, okay? You never use it in our practice or what? I don't think I ever use it in my work, but just there. Just name the formula, okay? Of course, the important thing is look at the example. I mean, let's look at the example that before we break, because I think it's good to see how it apply in practice. So this example is trying to do for this topic is look at the wage gap between men and women, okay? And look at all the data. Basically, men earn more than women, okay? And you want to see why, or you want to see there are many things different between men and women, right? Because men tend to work on jobs that actually require more manual work, right? And some women actually, as a housewife, or some women actually take care of kids, or some women have two different types of jobs. I mean, there's some difference, and maybe the occupational difference or age difference can make a difference, right? Because they usually, may say for China or other places, women retire earlier, right, compared to men in general. So that's why you need to see how do we do that. So how they do that is look at the US data, and they tell you that they use the CPS data, and there's many things. They clean up the data, try to control the age, try to control only the employed, exclude the self-employed. Is looking at people who just keep interview over 4 months. So a lot of data. So just to convince you this is a good thing. Okay. Although I skim over that, but actually this is very important. Remember our class 1 said garbage in, garbage out. To make sure that this is correct is the most important part of your analysis. If you don't get it right, then everything is wrong. Okay. But I'm just skimming through because I don't think I should spend time on reading sentence one by one, right? And the data is large. You can see it's almost like 100,000, 1,500,000 people. And they also need to control work hour because part-time job is a problematic, okay? So you can see how they present the data. Look at the percentile. In general, hourly wage men earn 17% more, right? and just look at the range, okay? And the highest difference comes from the center, the both sides, okay? Okay, and probably you want to run the regression, okay? And they decided it's not about the absolute change, but the percentage difference. So they look at the log function, okay? And they just regress what? Very simple, regress the wage over a binary variables, the 0 and 1. Okay, what does that mean? It just means the following. The binary actually means this, right? You have a regression, log W, okay? G is equal to 1 if female, right? 0 otherwise. Okay, what does that mean? It means the following. Just the regression set this is alpha, right? Because what we run is this, right? Alpha plus beta G, right? So when this is male, just alpha, right? And the female will be alpha plus beta, okay? Because beta negative, as you expect, right? So this is the case, okay? So that is the model we try to estimate when you run that, okay? Is that clear? Well, of course, there's actually, I don't know why I write the line there because there's nothing in the line, nothing in the horizontal. Actually, right? I should write it in this way, right? Alpha if female, alpha plus beta if female, alpha if male. I mean, probably I shouldn't write a scatter plot because nothing to scatter anyway. Okay, so that is the model they are looking at when D is a dummy, right? Because D is a binary, okay? And they figure out that actually female earn 30% less, okay? And then you want to look at the confidence interval, okay? Look at SE, and you can see the interval doesn't include 0, okay? So this is real, right? That's what you mean. And you can also do the confidence interval, right? As I said, right? 95% from here to here, right? Not include 0, so that's good. And what keep going is they want to look at some subsample, okay? Because that's usually what you do and do analysis. The big data, you run a regression, you figure out something there. You want to look at subsamples, right? Focus on, say, special cases, much smaller, higher wages. You also do the same, right? And figure out that this professional job actually has less wage gap, okay? And however, because this is small sample size, as you may expect, the interval actually from negative to positive, which includes 0. So we can't really rule out that the general gap for this small subsample. Okay, is that clear? So this is how you would do it. Okay, I mean the easiest look at the interval whether it includes 0 or not, right? The simplest because the same thing. Okay, I hope this makes things clear. Okay, and they try to say, I mean, the difference and okay, what happened? I mean, when you look at the mathematician and computer, you have a large sample, as you see, right? Well, we don't know what's going on unless we have more data, but at least that is what we can conclude, right? At least the gender gap in the computer and mathematical occupation, I think ITM belong to here. Okay, I don't know. Maybe you ask after graduate, is it men earn more than women? I don't know. I mean, you have to tell. And look at marketing research and marketing specialists. Okay, they're no different. Okay, not sure because this is rather imbalanced data, right? Because there's very few female, right? a lot of female here, so it's unclear the gender gap is there or not. But you can see how this being done. Look at how the CI, right? And you can judge how well it's being done. Okay. And what I try to say is you may need to collect more data if you can't tell, but I don't think that's a important thing, message to be there. Okay. I guess it's 45 minutes. I should take a break. Is that okay? Let's take a break. I will put up the quiz. You can do it again. Quiz doesn't start at 2:30, right? So I put a quiz. You can just try to do it. You can do the quiz after the break is over. Okay, only 10 questions of multiple choice. Okay. The blackboard. Oh, this is huge. Yeah. 大于小于2可以理解，大于2可以理解，或者小于负2可以理解。different from zero. Or look at the p value， 就是小于0.5这个不是因为本科学中没事就是这么简单的，就是这么简单，没有什么东西可以做。来谁？大過2或者細，absolute value 大過2啦 ，absolute value。咁咧點解？會咁講嘅意思講，佢哋都 describe， 然後係 Stephen will wonder why I see that喺度嘅。我感受嘅
就是我们有现在的非常，那我知道，就是不同的都是光是说我是很好，他有看，甚至是现在在的一个答我没错了，就是我要这样说了，就是在这里老我就是整班的，对，就我在网上就叫把它下来，冒走对啊，下周这样，他是哪个？他有。香港咧嗰個，即係因為個 data 成日我哋合作到啊嘛。哦，係啊，好冒險喎其實。即係假設如果有個人對呢啲做完嗰唔係個個人會對呢個人做咁如果假呢就會做得㗎啦。你按照你而家嗰個情況嚟，唔係跟住呢啲而家等住考評個人冇跟住喎，有得得㗎，有咩人讀啊？係有，但係3個字。打等咯，最後嗰個。哦，即係 I mean 呢個方法可能啲，我知但唔得最後啊嘛。我唔會，我等你做咗佢。因為想你哋睇下 collect 少 data 俾你感受一下。佢 data 我明，好少咗嘅，我知，唔會影響你個 grade 嘅。即係你就算 based on long data 或者 income 嗰啲係殘，我哋 TA 嘅非常之 capable 佢會搞掂。唔係擔心，就算你如果唔睇啲態度全部有關，係會都係咁噶啦，因為你係做咩嘅？我真係拉㗎啦，係咪？會方面。
The quiz officially start. You have 20 minutes to do it. 2 minutes for each question. So don't worry if you get half of correct, you get full credit. Okay, even if you don't, if you attempt it, you already get 1 mark. Okay, if you get more than half, then you get 3 marks. Okay. 10 minutes left, 10 minutes left. So don't worry if you more than half already get the full mark, okay? If you do it, you get 1 mark. You get more than half, you get 3, okay? And even if you don't get enough, then you can ask me. I can give you something that you can do. You can make up the marks, okay? So don't worry about that.
跟我讲，如果你拿4分的话，就如果你4分的话，会发现会给你一些东西做get back to get back to 我是一个贵之后最后一个可以的，给你做的是给你做下班。就为什么这个？但是我跟你说，那个会试题考试哪里的？我一般的话，应该考试要18分。如果第三天的，
2 minute, 2 minute, 2 minute, 2 minute. One minute, 1 minute, 1 minute, 1 minute. I guess you should submit now. It's time, so we go back to the class. So don't worry if you get more than 5, you get the full mark. But if you attempt, you get 1 point. So in case you're unlucky, fall below 4, let me know. If you want to get it back, I can assign you something you do and you can get back the point if you really want to do it. Okay, I can ask you to do something to get back the point if you really want to. But most of you would be able to get full point anyway. If you just happen to be not able to do it, I will probably ask you to do some more exercise to make it up. Okay, because the goal of this is not to make that you make sure you fail, but rather make sure you know what you don't know, right? And then make you read some books or notes and so on. Okay, so if you fall short of it, let me know. We are able to get it back. Okay. So now we have a confidence level and for the slope and intercept, right? But the thing we care actually is not the slope intercept, right? But we care about the y hat, the estimated value, right? So for estimate value, there are 2 things to estimate indeed. Okay, if you're an undergrad, you know the 2 things. One is the average of the y, right? We go back to the here. Go back to this one. Sorry for this one. For this one. This one, right? The line is indeed the average, right? Because there's an error term here, right? So the question is, first you want to say I give x. What is average of y? Is following will be coming from this one, right? But I also want to predict the individual value as well, right? So if you want to predict the average value of y, okay, that means that on average, I give you x, okay? There are multiple y, average of those. What is the prediction of that? That's a confidence interval. If I want to measure a particular point, not average, then I have to include this error term there. Then that will be the prediction interval. Okay? The idea is this: there are several sources of uncertainty here. First is alpha and beta, depending on data you got, right? That without that, there's a confidence interval. With this guy, you have the prediction interval. Okay? So later you will see the graph, and probably hopefully to convince you that they're different and the code will be different. We just start to run that. Okay? So I guess it's good to go over this code line by line, okay, and then see how to do it. Okay. Now the first one is very simple, right? NumP as NP, right? That's a simple thing. Second one is import stat API SM. Okay, that is a stat model, and I use NumP array. Okay, and as a to list, and I call the big X. It's a constant. That means that I add 1 to it. So the big X is a 2D array, right? With 1 in as a first column and this entry at the second. Okay. And here I create an OLS model, right? Using the stat model. Take an OLS string. I put in Y and X, put in the model. Okay. And the model I try to fit. Okay. Sorry, it's not robust. I just fit the normal one. Okay. If I put the covariance as robust, sorry, it's not robust. And then I just print the result. Okay. And maybe let me do that. I mean, you can take out your favorite Python. Let's do that. So you can go to the code lab. Or you can use whatever thing you like. It's also fine. Sign in my one. You can sign in your own. So you can use your own Python, IPython, Japan notebook, or whatever, Spider, whatever. if you like. Okay. So let me do it from scratch. Okay. As I emphasize, our class doesn't require any Python knowledge, so that's why we do it. Just copy. Okay. And so let's run this guy. A little bit. Okay. And remember, if we run this, you can look at the variables here. Okay. You can check out what kind of variable you got here. Okay. As you can see, x is a way, right? You have a 1 at the, that's how you would get add constant, add 1 to here. Okay. And the model we get is this guy, right? I think we get this here, right? Since I didn't do the robust, this is what I have, non-robust. Okay. And then as we said always look at the p-value or the t-value, right? Here you can't reject beta. That's how we check, right? Or you can check this guy, take this guy. That's done. Okay. And probably also want to check R square. So pretty good, right? Because we explain 50% of the data, right? But other than that, there's many things here, but we just use this one. We'll talk more later for other entry, but the entry I mentioned the thing you care, right? Of course, you can look at more, but it's the first step. Second step is look at the this slide. It's called CI. Okay. What I'm going to do is with this slightly some more new function we call linear space. Okay, linear space. What does that do? This actually create a array, a list of number, okay, from x the minimum number and x maximum number, and you get 100 of them. Okay, you look at the smaller x, bigger x, you divide into 100 small point, and you get each one of them. Is that clear? So basically, take the maximum value and minimum value, you cut 100 of them. Okay, and later let me run this line so that you know what we are doing. Okay, let's run this line in particular. This is a standard thing. I think you learned it in your summer as well, but let's run this line. So let's run this line. Later you will see why we do that. See, we have 100 number. You start from 1 and end with 7. Okay. You divide it into many small parts because the smallest x is 1, largest is 7. You cut it into 100 numbers, and this is a standard thing we do when you do plotting, right? Because you are going to do that. It's only useful for plotting, and we do prediction. Okay, this is the line. And the next one is at constant. I guess there's nothing new there. Do note that I have a capital X here, so make sure that you don't confuse the capital. And here comes the key thing here. This is key line is to get prediction. This will get the model to generate all the prediction required for our process. Okay, so I think it's a new function. It's not there like just a new function. I think they come out like 1 or 2 years old. It's not, I mean, relatively new, but it's already there. Okay, this is to get the prediction result. And that's simple. Once you get this object, prediction result stored there, you want to get the predicted mean, which is the y hat, right? So this is the y hat, right? Which is the you estimated alpha hat plus beta hat times x, right? And because you put this x, right? So just put all 100 number there, you predict the y. Is that clear? So just what we do is look at smallest x and biggest x. You draw 100 sample there, and you fit on the regression line, right? You get 100 data point there. Okay, is that clear what we're doing? And once I do that, I want to have a confidence interval. How I do that? This is a function also new. It's called confidence interval. Okay, and alpha is 95%. Is alpha here? Okay, and observation is false. Actually, I think it's if you don't write that, it's automatic default is false. And by false actually means confidence interval. And true, we will use in the next slide, is called prediction interval. Okay. When you try to predict the average value, it's an observation, so it's false. When I use true, will be used in the upcoming slide. Okay. And what this one gives you is a two-dimensional array. Each observation, you have lower bound, upper bound. Okay. So that's why I need to use this to get me the first column and the second one, the upper bound, lower bound. Okay. Let me run this code, and then you will see. Just copy here, and then you can check out the the variable and then you will see what does that mean here. Okay, let's run this, and then you will see what do we get. Okay, we'll check one by one, as I said. Okay, so X predict the capital letter, right? It's simply what we have, right? Just bunch of 1, and the other one is X is just 1 to 7. It's a divided in 100 point. Okay, and prediction result is the prediction. Where's the guy? Prediction result. Yeah, it's the guy. This guy you can see, you can't see it because it's a big object, contain many stuff. As I said, this is the central important point. You can check what they are. You can check the menu, but I will pick up the predicted mean, which is give you. You can see you have the prediction. You have 100 data point. Tell you each point what's the prediction. Okay, and look at the CI. CI here. You can see a two-dimensional array. Okay, it's lower interval, upper interval. Okay, so just to remind you what it is the following. It's simply this one, right? This is the point. You go to this range, right? And this is the CI lower. This is CI upper, right? And for each data point, right? From the minimum to the maximum, you divide into 100. Each one you go up here. You go find upper and lower. That's what I'm doing. Is that clear what I'm doing here? I hope it's clear, but if you don't know, ask me, because the Python code is right. It's nothing deep, right? Right? And there's no variation when you apply in your work. You just copy the code. The only change is Y and X, right? So, I mean, there's no need to think. Unless you want to get more result, you can check the menu, what kind of thing you want to get. But if you get is what I want to give you, then this is what you're doing. Is that clear? So there are a lot of things you don't need to worry, because everything is very standard. But different from your programming class, right? You need to think something. But this one, the procedure is all the same, right? You just need to change the data. Okay. Now, once I have this, right? Usually I want to visualize this, right? As a manager, right? You want to see the graph, right? So how to do the graph? All I do is our old friend Matplotlib. Okay, Matplotlib library. Okay, this is the first one, Matplotlib library. Okay, and the first line we have, as you would expect, is I want to do a scatter plot, which gives us the data. And the next one you would expect is simple, is I just based on the generate X, right? From X mean to X max and Y prediction. It's a line, the regression line. And here I use the plot, this new function called fill between. So I just want to highlight the thing. X and lower and upper, I use the gray color and fill it. And then the rest will be label X, coordinate X, Y, coordinate Y, the title, put there, add the legend and so. Okay? I don't think I need to go one by one, but I just copy the whole code and paste. Okay? I'm not going to type because I'm lazy. Well, I don't think you want me to type, right? Because I guess at this point or moment, you should be comfortable with the code already. Oh yeah, there's some problem with data is because of the I think there's some issue with the thing when I copy and paste, because of the copy of the PowerPoint, they do something, they change the quotation mark. Let me see what happened. Oh, still have this guy complaining. But it's good you see how I debug, right? Because that is the important point, is learn how to debug. Okay, so this is the line. You can see I have the dots and the red point and this common interval. You can see the closer the center is like squeeze, right? Because close center, you have more accurate measure. Outside is not so accurate. Let me remember the formula there. Okay? Is that okay? Is that clear? It's okay, because remember why it's more, because you remember the formula there since you are the further away from the mean, the S is higher, right? So that's why it's squeezed at the middle. Okay. The reason is because the data must pass through the center, right? The center, we have the most accurate measure. But beyond the center, the further away from the center, the interval is much larger. Because we have a confidence in the actually in the center, because that's most accurate one. The further away is less accurate. Okay. And you look at this one, right? This is the thing you see, right? And actually, just probably you would want to see this is this graph, right? This is the graph, right? And actually, it's not different from what usually you see. Let me look at that. Let me look at this one. Probably you want to look at all the time. I think it's good to look at now as well. So this is Hong Kong Observatory. Why I want to talk about this? Look at this guy, okay? And this guy probability. And this is very similar to what we see, right? I say, this is a interval estimate. Let me go back to the point estimate first, right? The point estimate is like this. So this is the point estimate, right? They tell you on average what the line is. Of course, at the background actually is a regression, but it's a very complicated regression. But the same idea here, right? And then they tell you the probability. Actually, it's the interval estimate, right? You can see the center is very accurate, right? Because look at the different color. Look at the bottom. It's actually confidence interval, right? Same idea, 90%, 80%, so on and so forth, right? Of course, you can plot different percentage as well if you want, right? I think given now your Python skills, you can draw different color interval estimate, right? 80%, 40%, you can draw different color and change it. That should not be difficult for you, given you do the Java so complicated, okay? This one, nothing, okay? Is that clear how we do it? Okay, this is the model. And here, as I try to convince you that if you do robust, then you just change this guy, everything goes on. Okay, just follow the same step and do everything. Okay, there's nothing, just only this only thing I mentioned. Okay, I don't think I need to talk more, right? Just do the same step. Okay, so let us finish this. Okay, now we have age and run the regression. Okay, we want to see how wage depend on age, and probably you ask why we regress age. Age is tracking experience. Okay, so you can see age actually affecting our data. And after the break, we'll talk about how age and gender put into the model, right? Because some of you during the previous break asked me why I just compare regress the gender, right? And just compare two mean, why we care. Because we also control age, right? Because in general, there are more older men than otherwise, right? So that's why you need to control that. So you can see when you run this regression, the interval is very small, right? So means that age, right? Pretty much you don't have much variation, right? So this is a very good, right? Because this interval is very small, so that's why actually it's very accurate, right? You have high confidence, this is actually true, right? And of course, you can't see it, but this is narrower than the outside, right? This mean is here. It's narrower than this. I don't know whether you can see, but is it clear? It's narrower than the outside. And some of you worry about age nonlinear. Look at this age over time, right? So you want to use contracted age square, and that is actually how economists do it. Okay, they would just use the age square. Okay, you look at all the papers that appear in literature. That's a standard thing. Okay, and of course you can use piecewise linear, you can use Lewis, whatever, but contracted is the thing you go. Okay, so now next is called predictive interval. Okay, the only difference is I said one more thing, one here. Okay, one common error term, as I mentioned, right? Because individual is epsilon. So compared to the previous one is one bigger. Okay, and as I mentioned, the code actually the same. Okay, the only difference is this guy true. Okay, you can see the only difference is true. CI, you can compare this only difference. Other thing the same. Okay, I'm not going to copy and paste to this. You can do it now, or you can do it whenever you feel comfortable. Okay, and the only change is I add. You can compare and contrast. There's a new line here, and there's only new line here. Okay, and I use yellow color for the PI. Okay, you can run it. Okay, you will see the PI is much larger. Okay, because there's a variation. Okay, and it's still, look at the data is still a little bit curved, but because curve is so small, you can't really see it. But that is that's the result we get. Okay, is that okay? So let me finish this slide because I think we have then we can talk. So quickly, okay. I don't think we need to talk too much, but the question would be, if one regression, it is we have a nice internal validity because when we check the hypothesis testing, R square everything look nice. The question is whether it apply to elsewhere because that's what we want to do, right? How we generalize, and the regression actually we never know. So that's why we have to be very careful about causality. Care about how it work in the future other places. But let's see the example. Hotel case. Okay. And remember the hotel case is starting from the first question, right? We want to see whether it holds, right? Because what we do is look at the data is the Vienna in November. So what do you want is look at other city, look at that type and see whether it still holds. Okay, that's standard thing you want to do, right? You look at the data, it works, you will try to apply to other data set, right? Other time, right? So you one more regression, okay? So what they do here is like try to look at the case instead of running regression, they look at the spine, right? Look at instead of running a simple regression, look at you decide to distinguish whether 2 miles is another slope, other 2 miles another one. Is that clear what you're doing here? Okay. You forget about this, be 2m, 2 miles, this is standard regression, right? And the other one more than just like the spine. I mean, this is what we learned last class already. This is same as this one. If you still not really worried there, we have this already. This is the one. We have this one already. Okay. So piecewise linear spine. Okay. And look at the graph. There's no graph. Okay. No graph. No graph. Okay. But why we do that? Because let's look at this. Okay. And they figure out that this is the following: alpha is 5, beta is negative, right? The further away from the city center, negative. But look at this, beyond 2 miles, actually very small. And then positive means crazy, right? The further away, it's more expensive slightly, right? but you try to look at the p-value. Okay. It's not there. Doesn't really matter anyway. Okay. So how do you read this? This is the usual table that you will read. Okay. And I think I have that. Later we'll call the star glazer. Later you will see. You output this table directly. And this is the table that you read every single journal, read every single book. This is the table you will see. Okay. How do we read that? I cannot pull anymore. Okay. So look at this. Look at the first one first. Okay. This is the data that November long weekday. Okay. This only different days. Okay. Look at this one is important because other the same thing. Okay. Look at this. This is negative. Okay. So if 2 star means P less than 0.5. Okay. Then we're done. Okay. This is more different from 0. Right. So this is okay. For this one, there's no star. So then just basically ignore. When you have star here, there's this constant, but usually you don't care about constant, doesn't really matter. And also like R square as well. Okay. And you can see the similar. Okay. So this is usually the thing we require you to know how to read. Okay. Here you can see robust standard error. You use the XC3. Okay. And this is automatically generate. Okay. And this is the thing that you should know how to do. And you expect I would give this kind of stuff in the test, the final exam, right? This is the thing you expect to know how to read. Okay, suppose I would ask, say, is this significant or not, right? And you can draw the conclusion, describe, okay? How the distance affecting the price, you can tell me, right? Within 2 miles, yeah, it's decreasing, right? And beyond 2 miles, it's not, right? If you look at the data for weekday, right? I think it's 1 more mile, then you drop by 31%, I guess. But depends on the I forgot the thing, but probably you can look at the log unit. It's log price, so it's 33% less, I guess. I mean, you have to check the data, but that's the idea, right? And then you also can compare across different days, right? It's pretty stable, right? So this is how you interpret. Okay, you can check how they interpret the result. Okay, and you can also look at the confidence level. Okay, and this is what regression would you do. Okay, you expected to run regression usually in this form, right? You run the whole data set. Okay, and you also subsample in the multiple pieces and try to see if the data has any irregularity there, right? Is the relationship only hold for weekday or weekend, right? You can see the November weekend has a much more higher coefficient, right? Compared to June weekend, okay? December don't have that much. Probably you can think about why, right? One possible reason is for December, a lot of people go, right? So even you further away, don't get to cut that much, right? Make sense, right? Of course, you have to figure out, you have to explain why you can see this, right? You have to explain why, say, for some reason, right? Because beyond 2 miles, then probably is not going to make a difference for people. You actually more than 2 miles, actually you have to drive. You rent a car, right? It's far away from the city, right? So that's why you don't see price difference from that. Right? Of course, we just only control the distance. And after the break, we talk about control more stuff. We call multiple regression. Then we have more things to say. Okay, let's have a break of 15 minutes. And then we come back, we talk about multiple regression.
透明，它就反向。
那问他们高是不是真的高？因为就是点开，然后超过都是点开。
透明的凹，一的话就不透明，零的话就完透明。
就看它比较凹嘛。
啊，零，这个凹嘛零也是零，那个一的话就如果你有按那 PS 或者凹到为零。
下面这个括号里。
括号标差。
哦 ，OK OK。有看到。
就有时候它是有地位的，对。我相信对讲的重要的嘛，你就是 X 做的地方，因为大概上就就是它的 X 交易，它的 X 方面是那个
应该是 R 的今天，应该是 R 的，只有 R 的。
好的，上点时间。
好像这是第一次在课上看到这个形式。是那个形式，一个形式。哦 ，OK OK，
这种是就沙子类关系，对啊，数量嘛。对，对，来提醒人。
确实。
现在大家都是见到那个形式，无论那是现他没有用 F。对，所以是问题。我觉得有点像，也不是像，
我比较喜欢这个还要打一些奇怪的。还要在另外构造。 会找你深入，还有该你其实比较好的。这个文字吗？还有都还没看，糟了，等他被抓跑，看的，做了。你说的是大题只有一些比较，它题里面要给他的大本里面有一些基本的哦，那要不会稍微写哦，因为他熟悉英文并在这个也和我他也是光我啊，增加，这个现在比较汇报。没有啊，刚刚说你要最后一个先出来啊，老师他没有参加那个，我就想聊一点他在乎的地方，就是深入见到因为他给个增加的模式，他们外观旁边更高的，他们有变化。哦，对，我上次忘记，我每次都以为他们后面的有点难理解。就是他是对的，他是他也一把好。啊，
那个像阿斯贵尔，它就会好一点。
Elsewhere 是有一点点多元有面板一般是 Elsewhere 的变化，没有你不主说面板。OK， 那像这种 Elsewhere， 像这里的 Elsewhere， 就连段垃圾哦，但是这个同一个很多东西 compare 很多东西是关于的你可以看到 Elsewhere， 所以说这个东西在 weekend 第二个因为那个被 Elsewhere 必须有大部分都一样的大家。
那不是只有说在别人网上人家吃这个东西，在别人去在晒一个因为欧那个在我们有一点 channel，
你 compare 这里 you are comparing 1, 2, 3, 4 and Elsewhere. In this case, the same thing but different. Elsewhere, this model fit with November we say that but your different X, different case, Elsewhere.
然后可以根据它 ask 说，为它目前拿到一个定量的数据，
就好一点的 compare 看到好一点。Absolutely 没有错。observation 係呢個absolutely 差，咁其實更加好啦。observation 就係更加必要嘅更加正咯。咁做 observation 係好大嘅 reason。如果你 observation 好大咧，就冇可能。这个东西这个 distance 已经很厉害的了，还很高的了，就只有2个 variable 都 expect 的话，很厉害。对。
那所以如果它 X 就是它去多大外的偏带，
对，所以可以说，因为它本身的意思就是说43%的 variation 跟还有它不是低量的，所以都给掉了。对，因为那个不是 question， 这个是所以大部分差不多是这样。第二个会发源。
哦，这个是吧？
如果他答应，那如果还是多大的责任，要是没有甚至你说的是更大，
没有一般我没有问一下2万，要不能接受1万，要不然我给你做一下。能做1、2个家庭，有没有 email？ GPT 啊，上面啊 ，email 的，GPT 好，没有问题。他哪个是说叫你他说了几句啊？他说如果你丢给他，他说了小的小组。打进去就丢一了呀 ，GPT 电话的也。
挂东西可以挂3个，
但是要对。
这个充电吗？所以我不用，我用丢一三高，丢一。就是那个被扫那个给你演示的那个，不是，它是另外一个大模型。哦，那个，也是，对，它也是它跟GPT 差不多的。
我马上下载。
下载网页版，这是网页版。我以为网页本身有，天天都在用啊，这个。
扎实点啊！
他问你，你觉得为什么 AI 有用？可以改进，现在给 comment， 之前我不给 comment 怎么来的？就是我打完后照片，他帮我加 comment。 每个公司自己打的，没有 加 comment 会加了一个东西，加其他的东西啊，就想想有这门课，而且临时拉不招的，所以我准备很多很小的一件，我觉得8月份还发的这个，前几个课可是没有水教啊。这么我会讲，我要把课里比较 P.H.D 的微观理论，博士班的微观理论，我没有教这些东西啊，其他不能教了，这个要没办法去美国就谁帮不了你。
我是不会觉得那个开水
啊？
我是不会觉得高级？
我这个是叫刘老师不给
哦，他教的讲
高考一点，
太恐怖了。
我直接介绍。第一个是真的不觉得，用他同学吧，对，都
好用，
好用，我习惯的。你可以先看一下。我觉得它唯一一点用就是必须 AI 的话，你必须要有东西跟那个，你给他让他多少块，他很难无中生有，他只能你做了80分，你就大概8分。东西完成你后面他做的话，你会经常如果你不小心的话，就比较变形。那不会杀死他，80%不给他。但是里边他做的，你主要70%、80%里边他90%。
阿生我有嘢係問佢，
你注意佢會錯嘅，你係記劇如果攞卡嘅，但係even program 攞卡嘅，
追唔出嚟？
啊呢個追你試下佢追，你試下將我哋嗰啲問題追啱。但係個結果就係佢成個係要將黑嘅，即係譬如話 confidence 就好咗嘅時候，驚佢睇落。你叫跑 P.I. 就真係錯嘅，其他你試下都。
喂，叫跑我為嗰個係我都係錯啦。
但係如果你知道佢點樣做咧，你想問加啲 comment 或者改啲嘢，你都爭佢。即係佢本身有嘢佢做，咁你有嘢咧。
阿生佢咁易應該唔係
我唔保證佢啱，根據我經驗嚟講，因為我試過佢做咧，佢同學都有睇翻咩嘢。有嗰陣時我哋嗰啲問題咧，所以要注意咯。
要注意啲波，
注意啲左右嘅。
那個好像說到就是做一些
只有他 GPT 3.5，今天我们老师可以随便用10个，但是就是你必须有东西给他，让他改英文，改英文就好。但是这个只有改英文就我觉得没什么，我觉得跟反应挺多的改英文。
我以前代碼嘅，
如果你時間太清楚，我要改的，很多時候比如說把它我直接拍一種，我自動都出來，把它這個 indentation 啊，在其他的
之前有看過一個例子，就是把東西餵給他，然後就問他一些，然後他說這個比較這段時間，
因為他長期的因為他之前做的創新內容需要很準備，後來過了幾個月之後，他就突然聽了很多，因為他不發現的時候，大家都，因為他理虧損了，對，所以你們解法，他這個法律才能那個解法，所以他的不是因為他不行，因為他可以跟企業版來講，它是一個為企業版的來講。还有1分鐘。多久吗？
我在香港没有现在，美国的，他已经回去了，还有些多吧，他这个我觉得这些多的那个一些零三年那个这个还得要还有应该出新的吧？我到底一些多呢？佢好多咁多嘢咧，之後但係我本身係之後第二個問題係我哋有沒有試過應用？是或者說有沒有試過使用這樣的去應用？應用感覺就需要做因為我這邊用的是預算的，嗰邊我教你這個東西沒有什麼用啊，看那個 regression 怎麼看，怎麼就跑了，這夠了嗎？那個已經，今天我既然不教我就不教了，我教的東西就是有用的，我如果不教的話，就真的其實可以當個人，我已經把這最精華的教你。你主要當然還是要是上手，當然那個人看習慣呀。OK，都係叫成大，佢奇怪怪哦。
Oh, it's not my choice. So last we won the regression. Okay. I don't know how you think about this class or this course, but some of you said, I mean, it's surprising that we have so many programming for this one. But since you guys are IT manager, so I think that it will be more rewarding to talk about Python and how to interpret that rather than I go to the mathematical property of here and there, right? But even the book we chose, right, is basically conceptual thing and the programming. So I hope that at least our class is you learn something from that. And I mean, as some of you have said, right, a lot of things have been many years you talk about econometrics or statistics. So I hope by doing homework and doing the quiz, help you to remind you what can be done, and especially your project. I think that would be the thing that would be most useful one. Please remember to fill in the your group member, because we need to decide whether it's enough and how to handle the timing issue. Okay. So multiple regression. Okay. As we have hinted, what we are doing here is we allow ourselves more than one variable x. Okay, we go from x1 up to xk. There's no limit what you can do. Okay, you can go for as long as you can do. And again, you still are minimizing the vertical distance from hyperplane concept. So if you consider a two-dimensional problem, right? So this is x1, this is x2, right? And you have dot in this three-dimensional space. You try to fit a plane, okay, such that this is just like you can imagine this is x1, this is x2, y is here. You try to fit the plane such that the vertical distance is minimized. Okay, same as the line. And although we cannot draw more than 2 dimensions, but conceptually, this is the hyperplane idea. Okay, and how to optimize this guy require matrix algebra or require multivariate calculus, which way beyond our scope. Okay, even the textbook has nothing. We put it there. So we believe we are IT manager, right? So I'm not, but you guys are the IT manager, right? So I mean, you believe the black box the computer gives you. So that's what we are doing. And the code we have in the Python actually extend to multivariate function, so there's no difficulties. Okay, and the only thing I want to mention here is what we call the omit variable bias, which essentially said, suppose your true model should be this one, but you estimate this one. Okay, what you will see is, I'm not going to do the proof, but you will see beta, which is the one you omit the x2, right, will be equal to beta 1, you move the other side, plus this guy. Maybe I write that down here because this is the beta, which is this guy, okay, will be equal to beta 1, which is this guy, plus delta beta 2, okay? So what does that mean here, okay? This is equal to itself plus how x2 and x1 related, okay? Delta is correlation coefficient between x1, x2, right? And you can see if this delta positive, right? Which means that x1, x2 are positive related, right? And beta is bigger than beta 1, right? Let me write that down here, right? If beta positive, beta 2 positive, right? So beta bigger than beta 1, right? Why? Because you run the regression, right? Some of the effect of x2 is absorbed into x1, right? So that's why it's bigger, okay? So that's why that's called the omit variable bias. Depends on how they're related, right? If this is negative, they're negative related, then this will be smaller, okay? So that's the only thing in this slide tells you by looking at this is what happens if you omit something, okay? If you omit the thing that is positive related, okay, and itself is positive, that will make us overestimate our parameter. Is that clear? And then this is the formula, okay? And the formula itself is not important, but I think that it would be, you understand conceptually, right? It depends on the product of this, right? If they multiply positive, then overestimate. Negative, negative estimate. Okay? And that can, why we need that? Because we never able to sure we can collect every single data. We may omit something. Then by looking at what you omit, then we can see how the coefficient change, right? Sometimes someone complain you omit something, but turn out to be you just maybe underestimate, overestimate, then you can tell people what the number is, right? So that would be the thing, but I guess we are not in competition, so that is something I just gloss over here. So in terms of measure notation, you can write, you don't have to care about which was, but I just put there because the book is like this. It's just, you put this as a matrix, you multiply that guy, okay? And then you inverse this guy, okay? I mean, you don't need to worry about this slide because I don't think anyone use it anyway, right? I don't even use it anyway, okay? I don't take this thing. And this is the regression, just like the covariance over variance, the same idea, okay? I'm not going to explain this. Here is the how to estimate coefficient, okay? And I don't know if I should explain this, but one thing I want to put there is this guy is same as simple regression. This guy the same. The only thing is this guy. Okay. And what's this guy? This guy is R squared if you regret xk over x. Okay. What does that mean? It means that if you try to run the regression, xk equal to alpha, beta, 1, right? And k minus 1, xk minus 1, and beta k plus 1, and k plus 1, and right? You try to use xk regress on others, okay? And why 1 minus r squared? The reason you can think is if this r squared is very big, right? That means that this one is represented by others, right? Because you can use this to give you this guy, okay? In that case, you cannot accurately estimate this, right? Because they are very similar, right? And when they're similar, then what you assign? Okay, suppose you can think in this way. You run a regression looking at income, right, on Y. X is your education. But if you include IQ, right, there, then they're very similar, right? Then you make your estimate less precise, right? Because you can't distinguish which one is more likely, right? So suppose the following, okay? You try to send a gift to your girlfriend or boyfriend, okay, for example. Say you try to send flowers, okay? She's happy, good, you can distinguish. And you send a diamond, you can distinguish, right? But what happens if you send a LV bag, handbag, and a bag from, I don't know, Burberry, okay? Then you can't distinguish properly, right? Because they're both very good, so you can't tell. Or you can send a flower, one type of flower, maybe rose, white rose, and then you send a red rose. You put it together, you can't distinguish which is which because they're so similar. Okay, so it means that if they're similar, you can't tell too much. That is what we call multicollinearity, right? When you run the regression, if they're so close to each other, you can't really tell because you need to put every time you need to put what the coefficient there, right? And if they're so close to each other, you can't really tell. Okay. And how to do S3 robust will be very difficult. We don't want to discuss. And the t-test, actually, we have been doing all the time. So there's nothing new there. The other new thing is here, you call the joint F test here, okay, which I'll talk about soon. But let's look at the data. Okay. So this is the data we have. First line, lumpy, there's nothing new. And pandas, okay? One is pandas. Pandas is a package where probably everyone you know, right? It's the one that you handle the data set. And usually with Excel, right? Use Panda to input, okay? And I create this, but if you use input from Excel or CSV, the data is already there, right? So this is the data, okay? So I convert a dictionary into the data frame, right? So that's what I'm doing. So let me do it. Let's do a multiple regression together. Okay. I run this regression. Now, here what we try to tell you is because when you try to run regression, right, multiple regression, then your data has many columns. Obviously, right? The data is usually more than what you pick. So the easiest way is not just Y and X. So you have to pick and choose. So the more common way is you have to define the formula and you write down the formula, run the regression from formula, right? Because your data can have X1, X2, X3, X4, X5, X7, right? So you don't want to use all. So you have to use the formula. It's a function that you do, okay? And data is the data we use, right? And same as below, okay? The only difference is I use ORS from formula rather than YX. Is that clear? Because this is the new thing, right? Because before I just ORS and YX, right? So that's the only difference. Is that clear? So we need this because of usually data has more column than what we need, right? Instead of try to create big X, we just have one big X and just call whatever we need, okay? And in that case, we just define the Panda package. We just call the package and put a formula there. The formula is a string. Is that okay? I hope that's not too difficult. Is that okay? I hope that is not. Given that you are doing Java, then I think that is something very simple, right? Because there's nothing to learn. I would say not nothing to learn, but nothing to worry because every time it's the same, right? So this is the formula. Okay. Let me do it again how to interpret this guy. the constant basically useless. Okay, not different from 0. This x1 less than 5%. So this okay. This one also okay. And this is common interval, right? And also you can draw the CI and PI, right? The same thing. The same code, every code you learned from previous lesson, but pre-topic, right? Beginning of the class, everything apply. You can draw the the same thing, okay? There's some changes to the code, but there's a similar. Okay. And what else? Yeah. So the next thing I want to talk about is what we call the package, very useful, called star glazer. The reason is that you will have different columns. You want to check different columns, how they work out, right? And in order to install star glazer in the code lab, you will use the pim pipe install function. Okay, let me do it first because it takes some time to run this code. Okay, so I just copy this guy, and you use Python. Then same, just install in your Python, then should be fine. But the one we use is in the code lab. Then we have to install on the fly, and let it install. Then once it's done, let me go back to the code here. So what we are doing is I still have the stat model, and the main thing is star glazer, dot star glazer, import star glazer. Okay, you ask me why, I don't know why this the code is this. Okay, I don't understand why he put it this way, but this is star glazer, dot star glazer, star glazer. Okay, I don't have any particular thing to say because this is the code that written by the guy, so I have to follow what they written. And here I have the data, and I separate two parts. There's data dictionary, I put it data frame, but you can put the same line. Okay, so let me copy that. Okay. Now it's successfully installed. Okay, and this is data. Okay, we are going to load it. Okay, and once we load the data, then we just, what I'm doing here is I going to feed, okay, two equations here. Okay, I feed two equations with the formula. I feed two different. This one use 1 and 2. This one use 1 and 3. Okay. Once I do it, I use a star glazer to put two model there, and put a title there and column, and that's one it. Okay. So that's the code. You can just basically change according to your need. Okay. And this gives you the model, right? You will see whether you have star or not. Okay. I think in this one we don't have any star because the model is pretty bad. But anyway, if your star actually gives you the star there. Okay. Is that okay? But this model has nothing, no star, so this is a very bad model. So this is because the data I give you is not very good. But anyway, but if you actually run the data, you will see something. Is that okay? So that's how you produce this kind of graph. Is that okay? Oh, that's fine. Now, this is the model. Okay. Now, what remain is trying to give you a practical case. Remember, we have seen the gender gap between men and women. We just said we didn't control the age, right? So now we are going to do more carefully. Okay. So the same data set, not going to repeat. The only difference is because before we have wage, female. Now we have wage, female, and age. Okay. Actually, we omit the age. Okay. And let's see what we get. Okay. And the calculation of age and female is actually negative. Okay, then what you expect is it the same as you expect? Okay, you run this. Okay, age is positive, right? So having the age make the female coefficient less, the gap, right? Okay, and if you raw age is like this. Okay, so that means that some of the at least 1% difference of the wage gap is explained by age, because you can imagine that man is older in the society, right? Because women tend to retire earlier, the US data. Okay, so that is the explanation. This is trying to explain the omit variable bias. Okay, the formula, but it's not important for us. I just keep there. We don't need to worry about that part, because the only thing we need to learn from the bias is more like the direction. But of course, you can do the calculation. Okay. And the next is, you can see the age is non-linear, right? You try to plot it. Okay. You can see more male older, as I said, right? More female is younger. Okay. And age is non-linear. So that what they do is they do the female age a square, age cube, and age cubic. Quarteric. And that's what you expect to see. And you can see, add one more square, help a little bit, but doesn't really help much, right? Because it just dropped from a little bit. Okay. And so probably age is not something there, but you can see doesn't do too much stuff. Okay, the effect of age. Is that okay? Now, the next thing we want to say is what we call the quantitative variables. Okay, and so far x is continuous, right? And but actually there's no assumption in the model saying x need not be continuous, right? X can be quantitative, yes or no, right? Because we have been doing female, right, and male, right? There's no. Then how can we do this? Is we will use a multiple dummy, right? Suppose I have variable have low, medium, high. Okay, and what we're going to do is to, when you have 3 category, you add 2 dummy. Okay, and you have dummy for medium, dummy for high. Okay, that means the following. In this simple model, okay, it means the following. It means that this is, if this is low, and this is medium, and this is high. So this is the way that, I mean, they think, right? Of course, you should add more stuff, but that's the way, right? This is what it means. Different intercept. Okay, because only 0 or 1. And in the one we have, we just change in the intercept, right? But you can do what we call the interaction variable, so that to change the slope. Okay, so let's see this. Okay, D you can think is like 0 or 1 is like male or female. Okay, you can put D here. Okay, and when D is 0, this is 0. Okay, right? When D is 1 is the bottom. So you can imagine this like this. D is maybe female. That will be X is age, right? Y is income. So that's what they're doing is beta 0, right? And this is beta 1, the slope, right? It's beta 0 plus beta 1, X. Okay, when D is 0, right? And you will have another one that turn out to be different intercept, right? Parallel. So same with B0 plus B2, beta 2 plus beta 1x. So this is beta 0 plus beta 1. Okay. And you can assume that it's parallel, just female, just make it higher. Okay. This level effect. If you assume the female only change the baseline of the wage, that's what you do. But also you can make it more complicated, not parallel. You can make it different slope. Okay. In that case, you are thinking that the male and the female, okay, the difference is this. This is beta 0 plus beta 1x, okay? And different slope will be asking, okay, this is beta 0, and this is beta 0 plus beta 2, okay? And the slope is all different. This is beta 0 plus beta 2 plus beta 1 of plus beta 3x. Okay, so this is here. Right? So you can allow this most general form to allow, say, female have different base wage. And also, according to this is their experience, right? As the age grow, female has different slope. So this is the more general form, right? So you interact means multiply with the continuous variable you have. Okay, and this is very standard in the when you if you still record undergrad thing, you do a lot of time. Okay, and many group the same idea, you can do the same. Okay, and lastly, you need not worry about the discrete or dummy variable. Even they are continuous, you can multiply. Okay, if you think it's not linear, right? The example like this, right? Look at the firm, and Y is revenue, X is global demand, X2 is financial health, and actually this thing need not be linear, so you have this. Okay, as mentioned. Okay, but the data will tell you. Okay. Lastly, probably want to mention interaction term. Okay, it's okay if we can't finish, we can finish the rest. But let me finish the interaction term. Okay, and this is the interaction thing. Here I use the MP array to do the multiply. Okay, but of course you can do the pandas. You can create new column. That should be fine. But here what I do is I have x1, x2, and I do the multiply, and I stack together, become a new x and a constant and run the regression. Okay, of course you can use the formula, and you just time multiply, you will still be done. Okay. And the output is the same, so it shouldn't be an issue to see that. Okay, and probably I want to go to this last single slide. Okay, so you can see that because this is very interesting. Look at what happened is when you have age, right, and look at the woman and the man. Look at all. This one is the best to look at, right? Actually, look at the female. By itself has no change intercept, right? So basically, female, when they have no experience, okay, actually there's no difference in their wages, okay? The changes actually coming from the growth rate, okay? It means that women, as they work, the wage growth is lower than men, okay? Initially, men and women have no difference in terms of wage, but men grows faster than women. That's what the regression tells you. Is that clear? So that is exactly tell you that the wage gap is not is increasing over time, but not by itself. Okay. And they consider the adding more stuff, non-linear, everything is the same. So at the end of the day, what they said is if you control many things, okay, the wage gap come from without control. You control more stuff, actually drop from 20% to 14%. So the more you control, actually this thing goes out. And that's what I want to say. Okay. We will talk about this next week. Okay. And there's nothing more.